Yeah, my method addresses this, but it's become extended into lots more things, all right? It's basically what she's saying here. So what we're going to do is the whole 9 yards today. Not the math, all right? Not the math. I told you that. This is related to something that has a lot of attention out there, and it's related to likelihood ratio analysis, all right? And here's a great book on it by Richard Royal from Hopkins, Likelihood in the title. And here's another book that's come out recently, Powhatan. I really love this book. Have you read this book? It's really good. It's really good. All right? Another book on likelihood. All right? Another book on likelihood. So I'm going to talk about likelihood because of the following. So for my first dollar, because nobody said anything yet, and you can stop me at any time, but let's get some going here. All right, who is that? Anybody know who that is? Fisher. There you go. Fisher gets the dollar. All right? It's Fisher. All right, so what has Fisher got? All right, so what's Fisher got to say about this? Well, this is Fisher, all right, and he believed whenever we can, we should use probability-based inference. Probability-based inference. Likelihood doesn't do that, all right? So what he said is using likelihood alone provides a weaker form of inference than probability-based inference. So if you're a likelihood ratio fan, I'm going to take exception to you because we get these high likelihoods, but we don't have a probability argument to go along with it. And you can have high likelihoods even with things that still have low probability. And I'll show you an example of that. All right? And this is all from Powhatan's book. It's really a great book. Another dollar.
Feynman.
Huh?
Feynman, Richard Feynman.
Who said? Oh, no, you don't get another one. No. You're not going to get rich on me. Yeah, this is Richard Feynman. So Richard Feynman is one of my heroes, all right? Richard Feynman, and what he said was, scientific knowledge is a body of statements of varying degrees of uncertainty. Oh, this is so nice for statisticians to hear from a physicist, okay? Some mostly unsure, some nearly sure, none absolutely certain. Those of us who are old enough, we remember the American Stat Association used to sell a t-shirt saying being a statistician is never having to say you're certain. All right, so here it is again, all right. March of science. So I've transferred this into something. I just did it for my teaching, and it's caught on, and people, they tell me I get credit for this, and it's sort of crazy because it's just this little gag that I do, but I call it the March of Science. And it's, we put now hypotheses on a probability scale. So here's the touch of Bayes coming in here, all right? So on a probability scale about whether or not the hypothesis is true, we can have mostly unsure down there. We can have nearly sure down there. We can have certain down at the end, but of course certain is also at the very beginning. We can be certain that the null hypothesis is not true, all right? So we're back to the stat fable again. And you remember the design. And we're going to base this on a paper because I want to make sure you understand that the foundation of this begins with a frequentist method. So this is a frequentist method to compare two proportions, a problem that's been around in statistics since the time of Pearson and before that and all that kind of stuff. Very hard problem, actually. Here's the latest paper that I know. It was published in December. So I'm at the beach in North Carolina. I get the PDF and look at this and say, oh, here's the latest paper on how do you compare two proportions. I'll program it into R and I'll make it the basis for this so people can see that it's based upon a frequentist method. All right? So here we go. It's based on a frequentist method. Now, here's the mortality difference, bias 266 versus usual care. And I've set up an essentially null interval. And I've set it up between a minus 2% difference and a 0% difference, thinking that if the difference is in there, it's not going to be worth anybody's effort to now take this into Africa or whatever it does. You can form any other essentially null interval you want. You can form an essentially null interval between that pixel and that pixel if you want. I don't care. It just needs to be an interval mathematically for me to make an argument. That's all. I'm just picking this one just for illustration. Now, the touch of Bayes comes in because we're going to put a prior probability in that interval. We're going to put 0.95 as a prior. I'm going to say, you know, I'm going to say 0.95 in there because I'll use the pointer, I don't use it much. We want some prudent scientific skepticism to come in here. Prudent scientific skepticism. What do we do as scientists? We start off thinking the null is true, And we have to make the data try to get us outside of that. Well, I'm coming with an essentially null interval. I'm going to put a 0.95 in there. And to make this look as close as possible to what we do in frequentist testing, guess what I'm going to do, of course? I'm going to put 0.25 and 0.25 in the two ends. You get it? This is where we start. This would be negotiated. This was a clinical trial. We'd talk to the FDA. We'd get our study sponsor on board. We'd set this down in paper, and we'd leave it. The entire rest of the process, everything else we do, is based upon a frequentist test statistic and the data. There's no other Bayesian stuff that goes in here. None. Zero. This is the beginning. Yeah?
When you make those probability assignments, I can understand 0.95 spread uniformly over the interval. How do you spread the 0.025 over the...
I'm not spreading it over. Everything I'm going to do is going to be based upon likelihood ratios of... I'm not going to go into the theory, but the likelihood ratio, suppose the result comes out over here, whatever the scale is, okay? I'm going to take the maximum likelihood estimate of the density here, and what you have to do is you have to come up with a non-centrality. You have to estimate the maximum likelihood for the non-centrality parameter. You take that, you compare it to that, and you compare it to that. That's how you're going to see the examples in a little bit. I'm not putting density over the whole range. Okay? I'm just saying it's either in that region, or that region, and I'm taking the maximum densities that I can get in those regions relative to the data. All right? That's the math behind it. But I've never shown the math to anybody. But it's basically a bunch of maximizations that goes on, and you have to do iterations in order to find out where things are and whatever. The math is not important here. The concept is important. All right? But you get $1 anyway.
Thanks.
So these are probabilities?
Another $1. Go ahead. These are prior probabilities.
So you would go to your funding and say that our probability is a 95% probability that we will find nothing?
95% probability that you're wrong. Okay? You think you're on the right track because you wouldn't be doing this study anyway, but your prudent scientific skepticism says, follow the example with me. You want to start here. You want to start with something that's against your notion, and then you want the data to overcome that. So let's do the example. You're right with me, believe me. These questions are the perfect questions. You're right with me, all right? But let's see what happens. Let's see what happens. Let's carry it through. This is where we start. Trial number one. Trial number one, the guy has the idea, I think this stuff will work. I got enough money to go to Africa, but it's the end of the rainy season. I'm going to go there. I'm going to set up a small tent. I'm going to give these kids this stuff, and let's see what happens. And so he gets about 70 in a group. He's got 21 that died in the BIOS 266 group, and he's got 31 that died in the usual care group. Simple? Simple? All right? And then this is all output from an R program that I have, okay? So what we have here is the sample size, all right? We've got the two proportions. You'll see the data come up in a little bit. We've got the estimate of the difference between the two proportions. The z-test based upon that article that I showed you from the American Statistician of December of 2010. We've got a p-value. We still have to have p-values. Damn it. All right? And we've got a confidence interval. So let's look at what it is. For this particular data, we've got proportions of 30% in one group and about 45% in the other group. Looks good, right? This is in the direction that we think things ought to go. All right? We get a test statistic that gives us a p-value, a z-statistic gives us a p-value of 0.07. Oh, it's non-significant. You know, it's just non-significant. That'll come back to haunt us if we're in the traditional world today. All right? And we got a confidence interval that goes from minus 0.304 to plus 0.01. And so I'd be saying to my students, why is this related to the p-value? Well, it contains 0, therefore, you know, blah, blah, blah. Okay? Don't have to do it with this group. Well, what we get out of that, in answer to your question through an example, is we get out Bayes factors for the three regions, okay? So these are the three regions compared to each other, taking the maximum density that we would have gotten, given the data, in each of the three regions and contrasting that. That's basically the crux of the theory, okay? So we've got the three regions, the superior region, the null region, and the inferior region, all right? And we got Bayes factors of 3.35 because it's over on the left-hand side. That's where it was, all right?
By Bayes factor, you mean the posterior for one of the three sets over what?
This is just the Bayes factor. This is just what is, okay, I got a result, okay? If I fit the best, in this case